In this chapter, I will introduce the concepts of physical quantities. Chemistry is the science that studies the properties of substances and the transformations they undergo. The properties can be classified as physical and chemical properties. The physical property of a substance is any property that is measurable, which describes a state. For example, color, mass, volume, and temperature are typical physical properties. A chemical property is any of a substance's properties that can be measured during or after a chemical reaction. That is, any property that can be established only by changing a substance's chemical identity. For example, flammability, oxidizing strength, toxicity, and corrosivity are typical chemical properties. A physical quantity of a substance is a physical or chemical property that can be quantified by measurement. For example, we can use our finger to feel the hotness of the cup, but a thermometer can quantify the temperature of the coffee. So, temperature is a physical quantity. The color is another example. Red, green, and blue are the qualitative descriptions of colors. In contrast, the wavelength or frequency of electromagnetic wave, or the energy of photons, is the physical quantity to describe the color of light. The International System of Quantities defines 7 base quantities. They are length, mass, time, electric current, temperature, amount of substance, and luminous intensity. The base quantities are independent of one another. All other physical quantities are regarded as being derived from these base quantities. For example, speed is the quotient of length and time. Physical quantities have conventionally assigned symbols, and we will use them throughout this course. To reduce ambiguity, in this course and most literatures, the symbols of quantities are in italic font. Physical quantities are often characterized as intensive and extensive quantities. An extensive quantity is a physical quantity which is additive for subsystems. For example, mass is an extensive quantity. The mass of the system composed of 2 objects with mass m is 2m. An intensive quantity does not depend on the size or extent of the system, nor on the amount of matter in the object. For example, temperature is an intensive quantity. The temperature of the system composed of 2 objects with temperature T is still T. A physical quantity can be composed of other physical quantities. The ratio of 2 extensive quantities is an intensive quantity. For example, the ratio of mass and volume, which are 2 extensive quantities, is density, which is an intensive quantity. The product of 2 intensive quantities is another intensive quantity. For example, the product of density and molar volume, which are 2 intensive quantities, is molar mass, which is another intensive quantity. Some physical quantities are neither intensive nor extensive, such as the square root of volume. The assignment of some quantities as intensive or extensive may depend on the way subsystems are arranged. For example, if 2 identical batteries are connected in parallel, the voltage of the system is equal to the voltage of each cell, while the electric current is extensive. However, if the same batteries are connected in series, the current becomes intensive and the voltage extensive. Fortunately, the quantities discussed in general chemistry usually do not have such ambiguity. A physical quantity can be expressed as a value, which is the algebraic multiplication of a numerical value and a unit. A unit is a particular quantity, defined and adopted by convention, with which other quantities of the same kind are compared in order to express their magnitudes relative to that quantity. Units have conventionally assigned symbols. A numerical value is the quotient of the value of a quantity and the unit used in its expression. Pay attention that a numerical value must be a pure number. Physical quantities are usually not pure numbers. For example, meter is a defined length. Its assigned symbol is lowercase m. A length of 6 times of meter is 6 meters. It is written as 6m. Here, 6 is the numerical value. Due to historical reasons, a physical quantity may have various units. For example, meter and inch are units of length. Meanwhile, temperature can be measured in Celsius, Fahrenheit, and Kelvin. To avoid confusion, we always use SI units in science. SI is the abbreviation of International System of Units in French. The SI system is a modern form of the metric system. It is coherent, so that you can convert between units easily. The SI unit is based on base units, derived units, and prefixes. Base units are the SI units for base quantities. They are meter, kilogram, second, ampere, Kelvin, mole, and candela. To avoid ambiguity, the symbols of the units are non-italic in this course and many other literatures. Pay attention to the base unit of mass. Though kilo is a prefix, kilogram is the base unit. All other physical units are regarded as being derived from these base units. For example, charge is the product of electric current and time. Thus, the SI unit of charge, coulomb, is the product of the unit of electric current, ampere, and the unit of time, second. Since SI system is coherent, there is no additional coefficient in this relationship. Pay attention, the names of SI units, when written in full, are always in lowercase. The symbols not named after persons are in lowercase. A derived unit is the measurement of a derived quantity. Derived units are expressed algebraically in terms of base units by means of the mathematical symbols of multiplication and division. Here, I show some derived quantities and their units. The definitions show their relationship with other quantities. For example, area is the square of length. So, the unit of area, square meter, is the square of the unit of the length, meter. The SI has special names for 22 derived units. Here, I list some of them. For example, Hertz, the SI unit of measurement of frequency if after German physicist Heinrich Rudolf Hertz, who first conclusively proved the existence of the electromagnetic waves. Pay attention, the full name of units named after persons are still in lowercase, but their symbols are written with an uppercase initial letter. For example, the symbol for Hertz is Hertz with uppercase H. Here, I show you some additional SI quantities and their units, which are often used in chemistry as well. Pay attention, energy and electric field strength share the symbol E. Such reuse of symbol is inevitable, because there are much more quantities in science than the Latin and Greek letters we can possibly use. So, make sure you know the quantity behind the symbol when you use it. To avoid very big or small numerical magnitude, prefixes can be used. A metric prefix is a unit prefix that precedes a basic unit of measure to indicate a multiple or submultiple of the unit. All metric prefixes used today are decadic. Each prefix has a unique symbol that is prepended to any unit symbol. The prefix kilo, for example, may be added to gram to indicate multiplication by 1,000. 1 kilogram is equal to 1,000 grams. The prefix milli, likewise, may be added to meter to indicate division by 1,000. 1 millimeter is equal to 1,000th of a meter. Here is an example of the relationship between cubic meter, cubic decameter, and cubic centimeter. There are also acceptable non-SI units. For example, plane angle is usually measured by degree. The size of atom is usually measured by angstrom. 1 angstrom is 0.1 nanometer. It is the typical size of atoms. Minute, hour, day, and year can be used for slow processes. Degree Celsius is often used for its convenience. The change of 1 degree Celsius is identical to the change of 1 Kelvin. 0 degrees Celsius is equal to 273.15 Kelvin. Liter and milliliter are usually used in chemistry to measure the volume of liquids. 1 liter is 1 cubic decimeter. 1 milliliter is 1 cubic centimeter. Cubic centimeter is also written as cc, but it is abandoned in modern science and is exclusively used in medicine. Finally, the mostly used unit for amount concentration is mole per liter, or molar. Its symbol is uppercase M. Other molar quantities are all based on this unit, such as molar volume and molar conductivity, etc. Energy has several widely used units beside its SI unit. An electronvolt, eV, is the measure of an amount of kinetic energy gained by a single electron accelerating from rest through an electric potential difference of 1 volt in vacuum. When used as a unit of energy, the numerical value of 1 eV in joule is equivalent to the numerical value of the charge of an electron in coulomb. The energies in atomic scale are usually measured in electron volts. Hartree is a unit of energy in quantum mechanics. A hartree is approximately the electric potential energy of the hydrogen atom in its ground state and twice its ionization energy. Calorie is an obsolete unit of energy. In physics and chemistry, the small calorie or gram calorie is the amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. Since the heat capacity of water depends on temperature, the value of 1 calorie is not determined. Thus, it is increasingly being superseded by the SI unit, the joule. Here, I show you an example of the conversion between joule, electronvolt, and hartree. Please check it by yourself.